Hello, class. Welcome to the last part of the lesson. I think it's lesson 7 about average rates of change and instantaneous rates of change. And today we will only solve the following problem, the problem that we started with actually, the problem of finding the velocity of an object at an instant, okay, at an instant of time. First, we have to define what that is. We have to understand the whole subtleties behind this problem. Okay, and we're gonna solve it for a particular particle or for a particular example, which is free fall. Okay, as you may know, free fall is basically when the kind of motion that happens when you let go of a body. Okay, for example, if you have a rock in your hand and you just let it go, the particle is gonna free fall. Okay, that's what we say, and basically it's gonna fall towards the ground, and as you know, it's gonna pick up velocity as it does so. Okay, it's gonna travel faster and faster and faster and faster. And so what we want to know is this: at a certain point in time, or at a certain position, okay, in the trajectory, what's gonna be the velocity, the instantaneous velocity right there. Okay, why cannot we talk about the velocity throughout the whole motion? Because this velocity always changes. What we can talk about is average velocities throughout the whole motion and instantaneous velocities. So let's see how this works. So first, what is the definition of velocity? We need to understand the definition of velocity in order to talk about it, right? So we're going to define average velocity in the following way. Suppose you have an object here on top of the x-axis. For example, this is my origin, this is the Mark 1, the Mark 2, etc., Mark 3, whatever. And so basically what the average velocity means is the following: it's just the change in x, the change in the position x of the particle over the change in time. And what that means is this: for example, let's suppose that your particle is here at time 0, okay, and then I'm going to exaggerate the scale. I'm going to say that this is the Mark 12. And you may think of this as meters, okay? Let's count space in meters, or length in meters, and time in seconds, for simplicity. So let's suppose that at time 0, which is my initial time, the particle is at an initial position of 0 meters, okay? So this is my first piece of data, so to speak. At time 0, the position is 0 meters. And then this object will travel along the x-axis, and at the end is going to be here. Okay, that's going to be its final position, 12. And let's suppose that 3 seconds have gone by. 3 seconds, okay? So the particle moves from here to here in 3 seconds, as you know, as you can see here. Okay, so what is its average velocity? What we do is simply calculate the change in x, and as you know by now, the change in x is defined as the final x minus the initial x. In this case, it's 12 minus 0, so that's going to be 12 meters. And what is the change in time? The change in time is the final time minus the initial time, which is 3 minus 0, which is 3 seconds. Okay, and then we divide these two changes. Okay, so basically what we're saying is that the average velocity, which is equal to this, is an average rate of change, because what we're saying is that when we divide these two quantities, 12 meters, let's actually do it. This is 12 meters and this is 3 seconds, and what we get is 4 meters per second. That's the average velocity of this particle in this situation. What that means is the following: that on average, as time passes 1 second, the change in position will be 4 meters on average. For this motion, on average, if 1 second goes by, then 4 meters will go by. That's what this means, on average. Does that mean that this particle always moves like in this way, like at a constant velocity of 4 meters per second? Nope. No, no, no. What it means is that on average, this is the velocity on average. Perhaps your particle traveled in this way. Look, like so, and then it stopped for a moment, and then it traveled very fast, and then it stopped for another moment, and then it went at a constant velocity, and then it stopped, and then arrived at the final position. You see how complex that motion was? In the end, this is the initial position, this is the final position, 0, 12. This particle traveled 12 meters in 3 seconds, and therefore this is its average velocity. You need to understand the concept of average velocity in this context. Okay, so that's what the average velocity is. It's just the rate, the average rate of change of the position against time. The average rate of change of position against time, or basically the change in position over the change in time. That's what we know as the average velocity. Perfect. So now that that's understood, let's go back to our main problem, which is, well, let me erase. Okay, it's the analysis of this motion. Let me tell you what this is. This is the graph of the function that represents free fall, more or less. Okay, look at this. F of t equals minus 5t squared. And as you can see in the y-axis, I'm writing y equals f of time, a function of time. And on the horizontal axis, I'm having, well, you don't see the t right there, but there must be a t in there for time. So basically what I'm describing here, guys, is that the following, okay? You may think of this function as the following situation. You have I don't know, you're on top of a very tall building, I don't know, let's say 500 meters or something, a very tall building. You have a particle, you're at the top of here at the roof, and then you have a particle like a coin or a rock, whatever, and you're gonna drop it. You're just gonna let go. The particle is gonna free fall, and your system of coordinates is laid down in the following way. I'm gonna do that in yellow. This is how your system of coordinates is laid down. Y, this is the position in Y, this is the position in X, so this is your 0, right there is your 0, and so the particle will have negative positions as time goes by. You see, when it drops a little bit of time, it's gonna be, let's say, at minus 5 meters, okay, and the minus 5 meters will represent that it's the negative sign means only that it's below this line of x. Okay, that's what it means. Don't, this is not nothing weird. Okay, and that's all of this is represented in this function. If you notice, for example, you can notice that at time 1, okay, the position in the y-axis is approximately, well, not approximately, it's going to be minus 5. You see, for time 1 second, the position is minus 5. For time 2 seconds, the position is minus 20 meters. For time 3 seconds, the position is minus 45 meters, and so on. So as you can see, this object is accelerating. It's traveling faster as time goes by. In 1 second here, it only went 5 meters downwards. And then in this other second, from 1 to 2, it went from here to here, and that's 15 meters downwards. So you see, its velocity is increasing, and that's why we want to analyze its velocity over these intervals of time and at a specific point. We're gonna solve all of these 3 tasks. Number 1, find the average velocity between initial time 1 second. Let's suppose again that this is seconds and this is meters. Initial time equals 1 second and final time equals 3 seconds. So let me locate my points of interest, which is this one and this other. Okay, this and this. Okay, and let's actually calculate the average velocity of this particle as time goes from 1 to 3 seconds. So let's do it. The average velocity is the change in the position, in this case in the y-axis, over a change in time. That is by definition the final position in y minus the initial position over the final time minus the initial time. What is the final position? As we can see, it's minus 45. And let's suppose that you didn't have the graph. What would you do? Well, just go to the function, right? Uh, the final position in y is obtained at the final position in time, which is 3 seconds, you see? And basically just put 3 seconds in here. So you're gonna get 3 to the square, which is 9 times minus 5 minus 45. That's how you can get the final position in y. And then minus, we have a minus the initial position in y, which is minus 5 over the final time, which is 3 seconds, and the initial time, which is 1. Okay, so let's calculate all of this. We're gonna get minus 40 over 2, which is minus 20 meters per second. So let's interpret this. What does this mean? Well, as the particle moves from second 1 to second 3 of all of this motion, it has an average velocity of minus 20 meters per second. That doesn't mean that it travels at that velocity throughout this interval. It means only on average it has this velocity. As 1 second goes by, the ball or whatever it's being dropped is traveling minus 20 meters. That's all it means. Okay, perfect. Now let's do the same. Find the average velocity between this other interval from an initial time of 1 and a final time of 2. So it's actually a smaller interval, right? Now it's not 2 seconds. It's now just 1 second. So let me erase these two lines. Now let me do this in red. So let's locate my points of interest. It's this one and this one. There you go. And let's calculate the average velocity of the particle in this interval only. So the change in position, y, over the change in time. Let's see the final position in y minus the initial position in y over the final time minus the initial time. What is the final position in y? Minus 20 minus the initial position in y, which is minus 5, over the change in time, which is 2 minus 1. We calculate all of this, we will get minus 15 over 1, and that's going to be, in the end, minus 15, right? Minus 15 meters per second. Okay, and that's the average velocity over this interval. And now, let me remind you what we are also doing at the same time, guys, even though we're not aware of that, maybe. What we are doing is basically the following. If you notice, if I drew the second line that goes through these 2 points, okay, this point and this point, let me draw the second line. Okay, more or less. Okay, if I draw the second line that goes through these 2 points, what does this mean? What delta y over delta t, what does this, which is equal to this, right? What does that mean? It means the slope of this line. The slope of this line is minus 15. Why? Because as you can see, this is your delta y. All of this is your delta y. This is your delta t, delta time. And so as we know, this is the rise. In this case, it's negative because it's going downwards. As you go from this point to this point, you're falling. Okay, so your rise is negative. And your run is always positive. So it's going from this point to this point. This is your run. So rise over run of this second line is the slope, and that's going to be equal to minus 15 because that's what we're doing. This is the rise over the run. You see? So basically, when you get the average velocity, when you have this type of function that gives you the position of a particle according to time, and then you locate 2 points, this point and this point, and you want to get the average velocity between these 2 points. Basically, what you are doing is well, you can think of this as drawing the second through those 2 points and finding the slope of that second. The slope. That slope will be the same as the average velocity. You see that it's 2 different ways of looking at this problem, or better, this is the geometrical way of looking at this problem. Okay, when you're told, hey, find the average velocity between this time and this time. Okay, fine, you locate those 2 points, you draw the second line that goes through those 2 points, you get the slope of that second line, and thus you have found the average velocity between those 2 points. Okay, unknowingly, you have found the average velocity. That's all there is to it. You see? Okay, so that is the geometrical interpretation. And let's go one step, well, not one step more. Let's go to the final conclusion of this process. Okay, if we do that, even close, we have calculated the average velocity from 1 second to 3 seconds. Okay, so from this point to this point, the average velocity between these 2 points. Fine, we got minus 20. Very good, very easy. Then we calculated the average velocity between this point, the same point, 1, and this other point in red. Okay, all we do is get draw the second line, get the slope, and that's the average velocity between these 2 points. Very well, very nice. And if I keep doing that, if I go like, okay, now let's find the average velocity between this point and maybe this other point, or maybe this other point, or maybe this other point, and basically we are sliding the point, this other variable point, towards this point. Okay, when we do that many more times and many more times, we will get, in the end, in the limiting process, we will get at basically being able to answer the following question. When we slide this point so much so that it's pretty much equal to 1 but different than 1, okay, as close as you want to this point 1 but still different, and we calculate the average velocity in that way, what we will be finding is this: the instantaneous velocity at time 1. Okay, that's all it means. That's what instantaneous velocity means at some time. If somebody asks you, find the instantaneous velocity of this object at time 1, what they're asking you basically is find the average velocity between this point and any other point, and then slide this point, this variable point, this is the fixed point, this is the variable point, slide this point more and more towards this point. Okay, and as this point is almost is pretty much right there, then at that time you can say that you have found the instantaneous velocity at t equals 1. And same idea, if we go back to our interpretation of the slopes, what we will be doing when we find the instantaneous velocity, basically if we go back to the slope of the tangent, that's what we will have. Okay, at that point, the instantaneous velocity will be correspondent to the slope of the tangent at that point. Okay, if the average velocity corresponds to the slope of the second, which is this, okay, the average velocity between this point and this point is represented by the slope of the second. Okay, then the instantaneous velocity at this point is represented geometrically as the slope of the tangent. Okay, the slope of the tangent, the slope of the second average velocity, slope of the tangent, instantaneous velocity at this point at time equals 1. And so how do we get the slope of a tangent line? How do we know that? With our derivative, okay? As we know, the derivative gives you that info. If you have a function and you have a point in that function and you want to calculate the slope of the tangent to the graph of that function at that precise point, all you do is take the function, get the derivative, f prime of t equals minus t. In this case, that's going to be my derivative, right? And evaluate such derivative in such point, which is in this case 1. So f prime of 1 will be equal to minus 10. What does this mean? What does this minus 10 mean? It's the slope of this tangent line. And going back to the interpretation of instantaneous velocity, the slope of this tangent line represents the instantaneous velocity of this particle at this point. You see, that's how we can play with the interpretations of the derivative, guys. You can think of the derivative as the slope of the tangent to a certain function, okay, at a certain point. And in that case, in which such function is giving you information about the position of a particle with respect to time, time should be here, okay? If that's the function that you have, then when you get the derivative of such function and you calculate it at a specific point, in this case, again, at t equals 1, what that derivative evaluated in such point will tell you is the instantaneous velocity of that object at this point. Okay, so find instantaneous velocity at time equals 1. Well, the instantaneous velocity is f prime evaluated in 1, and that's going to be minus 10 meters per second. This is the instantaneous velocity, and you can see that that it actually makes sense, right? If look, if the average velocity between 1 and 3 seconds is minus 20, and then the average velocity between 1 and 2 seconds is minus 15, you see it's kind of like following this pattern, right? From going downwards in 5 units, minus 20, minus 15, and then at that precise point at 1 you get minus 10 meters per second. You see, so it kind of like makes sense. And that's how you get the instantaneous velocity of a particle if you know its function of position. If you know the position of such object with respect to time, what you have to do is get the derivative of such function, evaluate the derivative in the time that you want to find the instantaneous velocity, and the thing that you get will be the instantaneous velocity of such particle. Let's see another example very quick, just for completion. Okay, suppose that you are told that certain object moves in the following way. Well, you are told that the position x of a particle is a function of time, okay? So basically x equals a function of time. And what is this function? Well, let's suppose that f of t equals 2t to the cube minus t squared, okay? It's a weird function, but it's perfectly valid. So this is how the position of this object changes with respect to time. It changes in this way: 2t to the cube minus t squared. Okay, so for example, the position at time 1 can be get by just evaluating in 1. The position will be 2 times 1 to the cube minus 1 to the square, which is going to be equal to 1. And then the position at 2 seconds will be equal to this. Okay, and so that's going to be 8 times 2, 16, minus 4 is going to be 12. Okay, 1 meter, 12 meters, etc. Okay, but this is the function when you evaluate it, when you evaluate t in the function itself, in f, what you're gonna get is the position of the particle, the position of the particle. Now, if you get the derivative of such function, f prime of t equals 8t to the square. Now it's gonna be 6t to the square minus 2t. This is the derivative. And if you evaluate the derivative at the same points, let's say 1 and 2, let's use the same points. What you're gonna get, let's first evaluate. We're gonna get 6 minus 2, that's 4, and then 6 to the square minus 2 times 2. We're gonna get 4 times 6, 24, minus 4, 20. What these numbers mean is the velocity, the instantaneous velocity, guys, of your particle at time 1 and at time 2 seconds. Okay, at time 1 the instantaneous velocity is 4 meters per second, and at time 2 the instantaneous velocity is 20 meters per second. And when you evaluate the function, only the function f, the original function, in those same times, what you're gonna get is the positions. You see the difference? So that's how this works. The concept of instantaneous velocity is basically obtained through the first derivative of a function of a position. Okay, we call this a function of position, when you can actually get the position of an object as a function of time. That is a function of position. And if you get the derivative of such function, you can find the instantaneous velocities at any time that you want. Okay, and that's how you solve this very old problem of the instantaneous velocity. So there it is, guys. There is nothing else to say. Thank you.